Good morning everyone. I am Sugunaselvarani, Assistant Professor, Department of Mathematics, CPA College, Bodinayakanur. Today we can see about some basic definitions in topology. Topology. Let X be a set and tau be a collection of subsets of X satisfying the following three axioms. Number 1, full set and the empty set belongs to tau. And number 2, if G1, G2 belongs to tau, then G1 intersection G2 belongs to tau. That is the finite intersection of elements of tau belongs to tau. And number 3, if G lambda belongs to tau, for every lambda belongs to A, where A is an arbitrary set, then the arbitrary union of elements of tau belongs to tau. Then tau is called the topology on X, and the members of tau are called the tau open sets, and the pair X, tau is called the topological space. The elements of X will be called the points of the space. Let us illustrate by an example. Take X is equal to set of A, B, C, and we can find all the possible topologies in it. First, take tau 1 is equal to set of phi, X, and check whether it satisfies the three conditions of topology. Number 1, phi, X belongs to tau 1, so it is obviously true. And number 2, phi intersection X is equal to X, that is equal to phi, that also belongs to tau 1. So, condition 2 is satisfied. And number 3, phi union X is equal to X, that belongs to tau 1. So, condition 3 is also satisfied. Hence, tau 1 satisfies all the three conditions of topology. So, tau 1 is the topology. Similarly, we can find other topologies also. Product topology. Let X be a topological space, and the product topology on X cross Y is a topology having as basis the collection script B of all sets of the form U cross V, where U is open in X and V is open in Y. Projection mapping. Let phi 1 from X cross Y to X be defined by phi 1 of X cross Y, X, Y is equal to X, and phi 2 from X cross Y to Y be defined by phi 2 of X, Y is equal to Y. The mappings phi 1 and phi 2 are called the projections of X cross Y onto its first and second factors respectively. Subspace topology. Let X be a topological space with topology tau, and Y is a subset of X. The collection tau Y is equal to set of Y intersection U, where U belongs to tau is a topology on Y called the subspace topology. Then Y is called the subspace of X, and its open set consists of all intersection of open sets of X with Y. Interior of A. Let X be a topological space with topology tau. Let A be a subset of X, and the interior of A is defined as the union of all open sets contained in A, and it's denoted by int A. Closure of A. Let X be a topological space with topology tau. Let A be a subset of X. Then the closure of A is defined as the intersection of all closed sets containing A, and it's denoted by CL of A or A bar. Interior versus closure. We can compare interior and closure. First one, interior of A is the largest open set contained in A, whereas closure of A is the smallest closed set contained in A. Next, interior is denoted as int A or A circle, and the closure of A is denoted as CL of A or A bar. Next, interior of A is contained in A, and A is contained in A closure. Next, if A is equal to open, if and only if A is equal to A interior and A is equal to closed, if and only if A is equal to A closure. Next, convex sets. Let Y be a subset of an ordered set X, then Y is convex in X if for each pair of points A is less than B of Y, the entire interval A, B of points of X lies in Y. Closed set. A subset A of a topological space X is said to be closed if the set X minus A is open. Limit points. If A is a subset of a topological space X, and if X is a point of X, then X is a limit point of A if every neighborhood of X intersects A in some point other than X itself. Hash-of spaces. A topological space X is called a hash-of space if for each pair of points x1, x2 of distinct points of X, there exist neighborhoods u1, u2 of x1, x2 respectively, they are disjoint. Thank you.